What specific problem does the Functional Generative Models, FGMs, aim to solve in the context of machine learning, particularly in relation to empirical risk minimization, ERM?
Functional Generative Models, FGMs, aim to address the limitations of empirical risk minimization, ERM, in modern machine learning, particularly when dealing with large and diverse datasets. ERM assumes a single function to model the relationship between inputs and outputs, which can lead to inefficiencies and poor generalization due to the complexity and variability of contemporary data. FGMs propose that each data point comes from its own unique function, thereby modeling the inherent noise and variability within the dataset more effectively. This approach allows FGMs to capture the functional noise associated with individual data points rather than relying solely on output noise, which is a limitation of ERM. By doing so, FGMs facilitate a more nuanced understanding of the data distribution and improve the generalization capabilities of machine learning models.
How does the proposed Functional Generative Models, FGMs, methodology work? Please illustrate this step by step, explaining how each data point is treated and how the corresponding function is assigned to it.
The proposed Functional Generative Models, FGMs methodology operates by treating each data point, x_i, y_i, as originating from its own unique function, f_theta_i, where y_i equals f_theta_i x_i, and theta_i is sampled from a distribution, p theta. This approach acknowledges that each data point may have its own underlying function, rather than assuming a single function applies to all data points, which is a limitation of traditional empirical risk minimization, ERM. The methodology begins by modeling the variability across the dataset as function noise, allowing for a more nuanced representation of the data. Each function, f_theta_i, is treated as a latent variable that captures the specific characteristics of the corresponding data point, thus enabling FGMs to account for the inherent noise and variability in the data. This results in a distribution over functions, which is fundamental to the functional risk minimization, FRM, framework derived from FGMs, allowing for more effective learning and generalization in diverse machine learning tasks.
Can you provide a simple yet illustrative example to demonstrate the inner workings of the FGMs? Walk through the main algorithm steps using this example.
To illustrate the workings of functional generative models, FGMs, consider a simple example where we have a dataset of house prices based on various features like size and location. In this scenario, each data point, x_i, y_i, represents a house where x_i includes features such as square footage and neighborhood, and y_i is the corresponding price. The FGM approach assigns a unique function, f_theta_i, to each house, capturing the specific relationship between its features and price expressed as y_i equals f_theta_i x_i. The main algorithm steps involve 1. Modeling each data point. For each house, we sample a parameter, theta_i, from a distribution, p theta, that reflects the variability in house pricing, allowing each house to have its own tailored function. 2. Training the model. Instead of finding a single function that fits all data points, we optimize the functions, f_theta_i, for each house to minimize the loss, which is now measured in function space rather than output space. 3. Evaluating performance. Finally, we assess the model's performance by predicting prices for unseen houses, leveraging the learned functions that account for the unique characteristics of each house, thus capturing the inherent noise and variability in the dataset. This process highlights how FGMs effectively model the complexity of real-world data by treating each data point as a distinct task.
What specific theoretical or practical benefits does the Functional Risk Minimization, FRM, framework offer over traditional ERM?
The Functional Risk Minimization, FRM, framework offers several specific theoretical and practical benefits over traditional empirical risk minimization, ERM. Firstly, FRM addresses the inefficiencies of ERM by modeling each data point with its own function, allowing for a more nuanced representation of variability within datasets, which is particularly important given the diverse nature of modern data. Secondly, FRM provides a clearer understanding of generalization in deep learning by considering a distribution over functions rather than a single privileged function, thus capturing function noise rather than just output noise. Additionally, FRM is linked to the generalization of over-parameterized neural networks, suggesting that it can better exploit the capacity of modern models. Empirically, FRM has shown advantages in various learning scenarios, outperforming ERM in tasks with complex noise structures, such as in value function estimation and representation learning with variational autoencoders, VAEs. Overall, FRM represents a fundamental shift in how we approach risk minimization in machine learning, making it more adaptable to the complexities of real-world data.
How is the effectiveness and validity of the FGMs and FRM assessed in the paper? What experimental designs, datasets, and metrics are used to evaluate their performance?
The effectiveness and validity of functional generative models, FGMs, and the Functional Risk Minimization, FRM, framework are assessed through various empirical experiments detailed in the paper. Specifically, the authors conduct experiments in supervised learning, unsupervised learning, and reinforcement learning, showcasing the advantages of FRM over traditional ERM. For instance, in the linear least squares analysis, they compare the performance of FRM and ERM under mean-squared error risk, demonstrating that FRM significantly outperforms ERM when noise is structured in the slope rather than the bias. Additionally, they evaluate FRM's performance in an offline value estimation task in the mountain car domain, where FRM outperforms ERM by over 20% in more challenging scenarios. Metrics used to evaluate performance include root mean square error, RMSE, for value function estimation and accuracy for classification tasks, particularly in the context of variational autoencoders, VAEs, applied to MNIST datasets with structured variations.
What limitations or potential drawbacks did the authors identify concerning the FRM framework and FGMs? How do these limitations impact their applicability in real-world scenarios?
The authors identified several limitations regarding the Functional Risk Minimization, FRM, framework, and Functional Generative Models, FGMs. One significant drawback is the computational challenge posed by high-dimensional integrals under nonlinear constraints, which can be difficult to manage in practice. Additionally, while FRM aims to model noise in function space, it may still struggle with the complexity of real-world data distributions, particularly when the underlying noise structure is intricate or poorly understood. The authors also noted that the reliance on over-parameterization, while beneficial in some contexts, could lead to inefficiencies or difficulties in generalization if not properly managed. These limitations suggest that while FRM and FGMs offer promising theoretical advantages, their practical implementation may require careful consideration of computational resources and the nature of the data being modeled.